My name is Dave Zilkoski. I will be moderating this presentation discussion on precise point positioning, or PPP. I've worked in the field of geodesy and surveying for over 50 years. I served as the director of the National Geodetic Survey and worked for the organization for almost 35 years. Today, I'm excited because we're going to talk about precise point positioning, or PPP, from a theoretical aspect to the practical aspect of PPP. We have two great speakers. Our first speaker is Dr. Jihye Park. She's an associate professor of geomatics in the School of Civil and Construction Engineering at Oregon State University. She holds a PhD in geodetic science and surveying from Ohio State University. Before joining Oregon State University, she worked as a research fellow at the University of Nottingham. Her research interests encompass GNSS positioning and navigation, GNSS reflectometry for sea level monitoring, which is very important, and also dealing with natural hazard assessments and artificial event analysis. She's also dedicated to geodesy, which is central to her research and teaching efforts of least square adjustments, GIS, and surveying for engineers. Dr. Park actively participates in the position, navigation, and timing community, PNT, through the Institute of Navigation, which is known as ION, and currently serves as a vice president for ION's Council Western Region. Our second speaker is just as impressive, Dr. Park&Weaver. He's an associate research professor of geomatics in the School of Civil and Construction Engineering at Oregon State University. He earned his Bachelor of Science and Master of Science in Civil Engineering with an emphasis in geomatics from Oregon State University. His PhD in Civil Engineering with an emphasis on GNSS geodesy from the University of Nottingham. He has collected and processed geospatial data using a wide range of technologies, including total stations, differential leveling, GNSS, UAS, and LiDAR. His research expertise include development of satellite radar altimetry and GNSS data processing algorithms for high accuracy applications and the alignment of geodetic data to the national reference frame, with a focus on mitigating errors in challenging environments, which is extremely important in today's world. His research contributions have supported new features widely used in National Geodetic Survey's tools, such as OpenSV data, which provide public access to high accuracy GNSS data processing and reference frame transformations. Dr. Weaver's current research interests include the development of precise point positioning algorithms to support real-time RTK GNSS users. You're going to hear a lot more about that today. So for now, let's turn over the presentation to Dr. Park.
Thank you, Dave, for the introduction. Let me share my screen first. All right, so let's start talking about the fundamental positioning concept of GNSS. The basis of GNSS is the trilateration surveying from the satellite. We can determine a position by using the distance measurement from 3 or more fixed anchors. Similarly, we use the distance between the satellites and the receiver. Of course, the distance measurements are made indirectly by measuring the travel time of the GNSS radio signal multiplied by the speed of light. That means the accurate timing is extremely important for GNSS positioning. So what's known is the position of each satellite that is obtained from the GNSS orbit information. What we measure is the travel distance of the signal, and we determine the receiver coordinate as well as the receiver clock error. The primary measurements of GNSS are carrier phase measurements, shown in phi here, and the code measurements, shown in P here. Carrier phase measurements are the raw carrier wave signals, and code measurements are modulated signals, shown in this red here, that has the unique pattern for each satellite. The left terms in both equations are what we measure, and the terms on the right-hand side include our primary unknown, the straight line distance between the satellite K and the receiver I, shown as a raw, And the rest of them are the errors like ionospheric error, tropospheric error, clock errors, phase ambiguities, integer phase frequency biases, multipath, and observational noise. I wouldn't go into the details about each term, but you can say that some terms are satellite dependent by having the superscript K. Some of them has the receiver dependent by having this subscript I, and some has the frequency terms like Q as a subscript. Then with those different characteristics, we apply different methods to either eliminate, mitigate, or extract those parameters from these GNSS signals. Another thing I would mention is the wavelengths of the carrier phase and the code observations. Obviously, the carrier phase has much shorter wavelengths than the code observations, as shown in here. The wavelengths of the carrier phase is about like 20 centimeters most of the time, while this wavelength of the code observation is about 3 meters. When we consider just 1% of the observational noise for each wavelength, each wave, then that makes like the 2 millimeter of observational noise from this carrier phase observation, and about like 30 centimeters of the observational noise for this code measurement. So that means the more precise observation then we can get from this carrier phase observation. It's pretty important because the more precise observation, then we guarantee more consistent and reliable measurements. However, the distance measurement may need to think about the ambiguity term in the carrier phase observations. The number of cycles in here between the satellite and the receivers provide the distance measurement, which is unknown, so we should estimate it. Once we correctly estimate the number of cycles of the phase, that is called the integer ambiguity, then you can guarantee the high precise solution throughout the surveying as long as there's no cycle slip or signal outage. However, the incorrectly fixed ambiguity may cause greater errors, so you need to be careful. If we assume that we are able to correctly determine the carrier phase ambiguity, then you can achieve highly accurate solution for positioning by using these carrier phase observations. GNSS measurements involve errors, just like any other surveying measurement. If you recall the type of errors, there are 3 types of errors: blunders, systematic errors, and random errors. When you assume that we wouldn't make any terrible mistake, then the major errors would be the systematic errors and the random error. The systematic errors are the errors you can explain their sources, such as like clock bias and drift for the clock error. They can be removed or reduced by using empirical models or by differencing direct observations. Random error is the observational noise that the occurrence of positive and negative errors are likely the same. Now, random errors can be mitigated by involving more observations. As mentioned earlier, the systematic errors can be reduced or completely eliminated by applying a proper strategy for each error. There are 4 types of error sources of GNSS signals. Satellite-based errors include the orbit error, satellite clock errors, and the phase windup. Propagation error includes the ionospheric and tropospheric effect, multipath, and intentional or unintentional interference. Receiver-based error include the receiver clock errors, interchannel biases, hardware, and antenna errors. Site-dependent errors include the tide effect. To obtain a highly precise and accurate solution, we need to reduce both systematic error and random errors. Using carrier phase observations, we can reduce the effect from this observational noise. the random error can be reduced by involving a lot of redundant observations, like having this multi-constellation GNSS that can add up the available observations. For the systematic errors, we can model the errors to subtract from the observation, or taking this difference between observations that can cancel out the common errors between the observations. There are different approaches to obtain the high accurate GNSS solution. As mentioned in the previous slide, carrier phase-based positioning would provide a higher precise solution than code-based positioning. How about this absolute positioning versus relative positioning? Absolute positioning, or a point positioning that uses one receiver, the one receiver need to deal with all these errors we saw in this previous slide. But when we have another receiver nearby, and this pair of receivers observe the same satellite, then we take the difference between the observations, and the common errors like clock errors are removed. This is the concept of the relative positioning. For the absolute positioning, there are two types. One is a standard point positioning, and the other one is a precise point positioning, or PPP. Both are the standalone positioning using a single set of equipment, while the standard point positioning relies on these redundant observations to mitigate not only these random errors, but all the other systematic errors. The precise point positioning uses this external information to model the errors and subtract this modeled errors quantity from each observations to deal with systematic error properly. Obviously, the PPP would be more accurate solution than the standard point positioning, because standard point positioning consider all the systematic errors like a random error. For the relative positioning, we can solve for a single baseline by having one reference station, or we can involve multiple stations in a network to better mitigate this atmospheric error. While this single baseline solution has a limitation for the baseline length, that is the distance between two receivers, the network-based positioning allows a longer baseline from a reference station by providing a wide range of atmospheric correction. One of the examples of single baseline versus the network solution would be the conventional RTK between one station and one rover versus the network RTK that provide the corrections from the network. In summary, there are roughly two methods to mitigate errors. First one is to use another station to cancel out common errors. That is the concept of this relative positioning. The second one is to apply the external information to correct error, and this is the concept of PPP. Let's dive into the PPP more detail in this lecture. The figure on the left effectively demonstrates what are involved in a GNSS radio signal transmitted from a satellite and a receiver to the receiver. Of course, these numbers are not really true, because they are all each errors depends on the specification of hardware, atmospheric conditions, like satellite geometry, and so on. But it still provides you some idea about this quantity of each error. I got this figure from this European Union Space Agency website, which can be really helpful to understand. But the purpose of PPP, I found that one error source is missing, which is the site-dependent error, because this tidal effect goes up to 50 centimeters. The goal of PPP is to achieve accurate position solution using undifferenced carrier phase and quarter pseudo range observation together with the precise orbit and clock information and the external sources. So the PPP does not need any other equipment, so it's a low-cost solution. And it's not limited by your baseline length, so it can be applied anywhere and anytime under different dynamics. It can be used in remote area without any GNSS network infrastructure. So it can be, and also it can be loaded to any platform. Let's look deeper how to apply the error corrections to PPP. The most critical error of GNSS positioning is the orbit and clock errors. Because the measurements are made from the satellite location, and we consider the satellite location at a certain time is given, the error in the orbit directly affects this range measurement. Also, the range observations are obtained by measuring the signal travel time multiplied by the speed of light. That is about 300 million meters per second. So extremely small clock errors could lead a huge error on the distance measurement. That's why many PPP services primarily focus on this orbit and clock corrections to provide users. Thankfully, there are different levels of orbit and clock products available. What we receive directly from the GNSS signal is the broadcast to orbit and clock information, and which is right here. And the accuracy is about 100 centimeter for orbit and up to 5 nanoseconds for the clock. 5 nanoseconds multiplied by the speed of light would be about 1.5 meter distance error. International GNSS service provides a precise product, from this ultra rapid to the final product of those two error corrections. As you see from the table, the accuracy dramatically improves when you use this final product. The trade-off is the latency of the data. Because of this processing and the validation time under the agency, so for the final product, you can use this product after 12 to up to 18 days after your data collection. Ionosphere is the ionized layer of the Earth's upper atmosphere. The electrons in the ionosphere generate the propagation errors to the GNSS radio signals. The electron content generates a delay on the code observation, and it makes the phase signal advanced. The magnitude of the ionosphere error could be up to 150 meters near the horizon. But the good news is that the 99% of ionospheric delay can be computed by using the a pretty simple linear combination of the equation of the signal. The propagation delay depends on the total electron content along the signal path and on the frequency on the signal itself, shown as F in here, as well as this geographic location and time. There are two ways of ionospheric corrections. One is to eliminate the first-order ionospheric delay by combining dual frequency signals. That's so-called ionosphere-free linear combination. This approach is pretty common for the PPP because it guarantees removing 99% of ionospheric delay. Another method is to apply TEC values from external products if the receiver only records a single frequency measurement. Although it's not common for the PPP, the single frequency users can utilize the ionospheric product provided by the IGS. This is an example for this, the ionospheric product, so-called Ionosphere on this left-hand side, that provides the total electron content over the world with this temporal resolution of 2 hours and the spatial resolution of 5 degrees in longitude and 2.5 degrees in latitude, as shown in this map. There are several regional TEC products available for this with the higher temporal and spatial resolution. A tropospheric delay is the signal delay caused by the lower atmospheric constituent. Unlike this ionospheric delay, the tropospheric delay is not frequency dependent and makes it a little difficult to extract from the signal by combining different frequency observation. Instead of indicating the signal delay on this ray path, it's usually expressed as a product of a zenith delay and a mapping function. A generic mapping function represents a relation between zenith effect at the observation site and the elevation angle of the signal. The tropospheric delay are defined by 2 categories. One is the hydrostatic delay in here, and the other one is the wet component. So the hydrostatic delay is considered as a dry component of the signal, and wet delay is a wet component of the signal, like a humidity. The total delay along the line of sight here is the sum of the dry delay and the wet delay. And we have like zenith hydrostatic delay as a model along the zenith direction, multiplied by the mapping function for the dry component as a function of the elevation angle, and to adding the zenith wet delay model multiplied by the mapping function for the wet component as a function of the elevation. The models and the mapping functions for these dry components are well developed and pretty straightforward because the stable characteristics of this dry component. But the wet component has a lot of randomness behavior. So that's why a lot of PPP processing algorithms apply these dry models, but the wet components tend to be estimated from the observation. There are 3 types of tidal corrections. Solid Earth tide effect is the site displacement caused by the tidal effect of the gravitational force from the sun and the moon, and it's up to the several tens of centimeters. It can be computed by this physical model as a function of the time and the location of the site. Ocean tide loading and pole tide loading are relatively indirect effects, and the magnitude is millimeter level. They are also the function of time and the location. The Earth's rotation should be taken into account because the Earth rotates while the GNSS signal travels from the space to the ground. The approximate travel time of the signal from a satellite to the ground is about 0.07 seconds, which is a really short time. But if you consider the movement of one point near the equator during this travel time of 0.07 second, it's already 32 meters approximately of the movement. So that's why we should apply the Earth's rotation rate for this correction. Another type of error is the relative effect. This is like a relative clock effect. One is a relativistic clock effect. Clocks are at a high altitude above the Earth running faster than clocks on the surface because of this the gravity effect. Also, the clocks moving from the high with this high velocity runs slower than the clock moving with the lower velocity. So considering this satellite altitude about like 20,000 kilometers above the Earth and the velocity of the satellite, these relativistic clock corrections can be computed. Relativistic range correction is also related to the Earth's gravity effect that affecting the speed because the speed of light changes, propagates, that near the surface are affected by the gravity more than the signal like at the high altitude. However, the relativistic range correction is much smaller and much less significant than this clock effect. Antenna phase center offset and the variation need to be corrected for both satellite and the receiver antennas. While we consider the satellite position based on this predefined antenna reference point, the signal is transmitted from this phase center on this satellite side and received to the phase center on the receiver side. The actual electrical antenna phase center varies with the elevation, azimuth, intensity of the signal, satellite signals, and frequency of the signal. The satellite antenna phase center offset and this phase center variation, PCO, PCB, they are published per satellite and frequency. For the satellite side and for the receiver side, these antenna calibrations are made for different models, brand, and manufacturer of the receiver. So this antenna correction information is also available through like so-called antex file. So far, we reviewed these different PPP corrections. Here I would like to quantify the effect of corrections using one of GNSS stations in Australia. The station ID is the ALIC, this station is capable of recording the full GNSS constellations. We used our in-house PPP engine to have a static point positioning solution with the different processing options. Here is the summary of this processing result. From the top to the bottom, we started with the standard point positioning using the default broadcast orbit and clock information without involving any other corrections. Then we added one or more PPP, like we accumulate the corrections, PPP corrections, as shown in this leftmost columns on the table. The static solution results of 1 day, like 24 hours of data, are shown as like north, east, and up components of error, as shown as D and DE, DU, for the standard and or with their standard deviation and the convergence time of each error component. The processing is done by using all 4 constellations of GPS, Galileo, GLONASS, and Beidou. As you see, the very basic standard point positioning result is about like 77 centimeter of error for the 3-dimensional components, 3D component, up to, and the convergence time is up to like several hours, which is quite slow. Then we added the precise clock, orbit and clock product that dramatically reduced the convergence time to be about like 30 minutes, and the mean errors became like a 30 centimeter. Adding differential code bias, antenna corrections, they didn't show a notable improvement so far, but as soon as we added the tight corrections, the error became like 1 centimeter. Adding this phase wind-up relativistic path corrections made some changes, but not significant as much as the others, the tight corrections. But this certainly shows the impact of the PPP corrections for the same data set. This table shows this comparison between the solution of single constellation GPS only versus the multiple constellations. While the error level would not be significantly different, the convergence time is improved by involving multiple constellations that contributed to mitigate the errors. I will stop here and let's move to the next speaker's presentation.
Thanks, Jihye. Thanks for the nice introduction, Dave. Well, thanks everybody for joining this session. I'll cover a little bit more of the practical side for PPP, following up Jihye's talk, but more of the theoretical and modeling part. But I thought it would be nice to start with, where does PPP fit in this large positioning spectrum for GNSS technologies. And from this table here, we can see that PPP is a single receiver dual frequency positioning approach that can be done on a global scale. It can achieve Jihye, which was mentioned, less than 10 centimeter accuracy after some initial convergence time has been reached. It's a little bit hard to appreciate what PPP is in terms of its excellent precision without first talking about the standard or single point positioning SPP approach. So this is hopefully going to reveal what makes PPP precise, because on the left-hand side, we have the standard point positioning approach where carrier phase information is not included in the positioning model, leaving only the code measurement information. That left-hand figure is showing for the scattered markers, the per epoch position estimation for those code-only measurements, and then the lines are the filtered or accumulated position across multiple epochs. So on the left side, we have around meter level or so position accuracy, when we're looking at individual epochs without the carrier phase. And on the right-hand side figure, after we go into this precise point positioning domain, we're now down at around a millimeter level for this configuration, which is GPS and Galileo satellites in a static positioning model. So the question is, how do we go from that relatively imprecise single or standard point positioning to this very precise PPP approach? Here, one of the major components is the inclusion of the precise carrier phase information in the positioning model. One consideration to be aware of for PPP is that we are not constraining the position of a reference station as is done for the RTK or network RTK processing that you might be familiar with. Instead, we're just relying on those precise satellite products that our previous speaker had talked about. That does impact the PPP user because those satellite positions are constrained within their reference frame. That's typically ITRF. For the user side, that means that the PPP user's reference frame inherits that ITRF, International Terrestrial Reference Frame. Those satellite positions have improved over time. The left side figure is showing our the International GNSS Service analysis centers, which are responsible for estimating those precise satellite products. In general, now we're down at around 2.5 centimeter level orbit accuracy, with even better precisions. But the key point here is that the PPP user becomes constrained into the reference frame of these satellites. And as conceptually, it can be thought of as an inheritance of the satellite reference frame to the user. So we already talked about the precise products and showed the difference between excluding and including the precise carrier phase. But just to give you some idea on how precise this carrier phase measurement is, this left side figure is showing the code measurement precision for comparison in terms of the modeled code measurement noise. And that's ranging from around 50 centimeters up to several meters. And then for the carrier phase measurement noise on the right-hand side, again, the modeled noise, it's ranging from around 2 millimeters up to around 12 millimeters. So the key to precise point positioning, the emphasis on precise, is due to that very precise carrier phase measurement being included in the model, and then also those high precision satellite products. The carrier phase is a little bit tricky to think about. So I wanted to give a little bit of visualization here. For GNSS measurements, we have information that is modulated on a carrier signal. So the carrier phase is conceptually the underlying sinusoidal signal, the second row in this animated figure here, which carries no information. But we would like to use its excellent precision for PPP. It's not as straightforward to use the carrier phase for positioning as it is for the towed measurement data, because we have this rather pesky ambiguity term that needs to be considered. This one is essentially an integer number of full wavelengths or cycles that have occurred between the transmission and reception of the signal. And the carrier phase measurement, the thing that we can observe, is actually only this orange colored or red colored part on the lower right. That's the partial phase of that carrier signal. So without estimating that N term, the integer ambiguity for the carrier phase, we are unable to fully unlock its potential and use the carrier phase as if it were a pseudo ring. So those are some of the additional details for PPP and how it operates. But now we'll move into different configurations for PPP. The two common configurations are static and kinematic, the left and right side figures here. For the static PPP user, their position is estimated as stationary, meaning that between consecutive epochs, position was assumed to remain the same for the static case. And then for the kinematic case on the right-hand side, we do not constrain the user's position in time. This means that the kinematic user, their position is assumed to be non-stationary and is free to move around between epochs. So getting to the fun part, I'd like to give some idea on the static PPP performance. So this is where the user position is constrained in time. We're assuming the user position is stationary. So this would be more applicable to something like a core station. And in this case, we're looking at two IGS stations, defined by the rows on these figures, with their 2D position error as the left column and 3D position error as the right column. The positioning results shown here are excluding the first 1 hour of processing time on each day, where we expect large position errors due to an initial convergence period, which I will talk about afterwards. The results on this slide and the next slide are using GPS and Galileo measurements at 30-second rate, everything CNES, precise satellite products. So you can You can see some spikes in these figures at the start of each day, and those ones correspond to some remaining position error amplification from that initial convergence period. And that initial convergence period is repeated on each day because the processing is set up to process each day independently. So at the start of each day, you have some that goes remaining convergence artifacts. But regardless, we're computing the overall statistics for the mean 2D and 3D position accuracies, summarizing those on the table on the right side there. For the static PPP case, we're down at around 2 to 4 millimeters for the 2D position accuracy and around 4 to 6 millimeters for the 3D position accuracy. For the kinematic PPP case, which might be a little bit more interesting, especially if you're not a TORS user. This configuration allows the position to move between epochs, so we're not constraining information on the user's position in time. That means that we have a little bit of a weaker model because we have more unconstrained parameters to deal with. But we can still achieve relatively precise position for the kinematic user. So the same data were processed in the kinematic mode, and we are getting around 1 centimeter or so for the 2D position accuracy in terms of the mean value. Similarly, for the 3D position accuracy, we're around 2 to 3 centimeters here. And those are the overall mean values. So depending on the time of day and satellite geometry, we might be more or less than that even. But overall, those are the accuracies that we can expect in kinematic case under ideal conditions. The initial convergence time for PPP is something that you might not be very familiar with if your experience is mostly in the differential RTK, network RTK world, because things happen. The convergence interval there is almost non-existent. But for PPP, because we're using those ambiguous carrier phase measurements, our position estimation is affected by this sometimes lengthy initial convergence time. So what that really is a period from the beginning of the processing where those ambiguities are not estimated precisely. So the position solution was relying more on the code measurements, which are much more noisy than the carrier phase. And after we've accumulated enough measurements, typically less than an hour is required, those carrier phase ambiguities are estimated precisely, and the solution converges down to the precision of the carrier phase measurements rather than the precision of those noisy code measurements. So that's what's shown on the figure here up till around 13 minutes in this case. That's what the CT1 label is shown to get to 5 centimeter horizontal precision. Our solution is mostly dependent on those noisy code measurements. And then afterward, those carrier phase ambiguities are estimated precisely. We've fully unlocked the high precision carrier phase measurements. For real-time users, that initial convergence interval is very problematic because you're essentially waiting to achieve that high precision solution. But fortunately, there are some processing steps that can be done to reduce that initial convergence time. One of the main processing techniques is integer ambiguity resolution. On the left side figure, the float or non-integer ambiguity solution is shown, and then on the right side figure, the same processing is done, but with fixed integer ambiguities. The different colors on this figure represent GPS only for the blue line, or different combinations of constellations like GPS Galileo for the red line, all the way up to the 4 system one for the purple line, GPS Galileo, Beidou, and Lonas. So here on the left side figure, we can see some improvement on that initial convergence time for the float solution after including more than one system. So that's a great first step for the PPP user to reduce that potentially lengthy convergence interval. But the real benefit comes from the integer ambiguity resolution part on the right side figure, especially when we do integer ambiguity resolution for the multi-system cases. And this is a little bit of an extension of the traditional PPP case, where traditional PPP would keep ambiguities as float values on the left side figure. But if additional satellite products and complex algorithms are included, then it's possible to deal with biases that would otherwise destroy the integer nature of those ambiguity parameters. That allows for the fixed solution on the right side figure. In relatively recent years, more services have been made available for PPP, either in real time or post-processing. I put a few together in this table, which is incomplete. It's very even lower than what's listed here. But I wanted to highlight some of the differences between services like Point Perfect, Central Point RTX, TerraStar. Those are commercial services, paid services that are available from different companies. But there are also some public services like the Galileo High Accuracy Service that enables real-time PPP, or the GNSS service, which is a regional one rather than a global one, and also this public Canadian Spatial Reference System PPP service from Natural Resources Canada that is a post-processing PPP service on a global scale. So next, I'll highlight a couple of these to give some idea on their performance. This figure is showing the CSRS-PPP service, a combination of their internal processing was summarized in this figure. There are a lot more helpful figures if you want to follow this link provided here. But this online post-processing service by Natural Resources Canada allows users to upload a Brinex file and process in static and kinematic PPP configurations. And recent updates have also included integer ambiguity resolution or ambiguity resolution, which is abbreviated as PPP-AR. in this figure is highlighting some of the improvements that are made as the software is basically updated to improve different processing algorithms and strategies, like the inclusion of Galileo satellites in this latest version of the software. So you can expect around a 2 centimeter or 2 centimeter or so position accuracy on the latest version under ideal conditions for this tool. And then that's assuming you have at least 1 hour of measurements available in your INX file with more infrequent as the session length has increased. So as more observations are available in your INX files. These figures are from a experimental real-time PPP software that evaluated different positioning scenarios. So the top left figure is an open sky environment, and the right figure are positioned with kinematic PPP highways, and lower left figure is when tunnels are encountered, and the lower right figure are urban canyons. So this real-time kinematic PPP, the authors actually did include more analysis on integrating GNSS part with inertial measurements, so IMQ. But for now, what I'm showing here are the ideal performance for the kinematic PPPs are on the top left. And then on the top right side, those spikes in the positioning time series correspond to driving under some overpasses. So signal users walk. And there's a brief reconvergence period. Typically, in this case, it's only an epoch or two to get back down to that centimeter level precision. And then tunnels, of course, no satellites are visible, so without the inertial measurements, the GNSS only position is very unreliable or not existent at all. Some data gaps. And then the urban canyon conditions are especially challenging due to limited satellite visibility and the multipath. So the key takeaway here is that real-time kinematic PPP with open sky conditions is very successful in achieving per centimeter level precision, but there are certain conditions which, if you are using inertial measurements, you need to watch out for, because the position error can be amplified just as it would for other positioning techniques if you don't have satellite visibility or large evolution of precision scenarios. The Galileo High Accuracy Service is currently at service level 1 and is available everywhere at different accuracy levels. But for this experiment that was done, these authors evaluated the Galileo High Accuracy Service under ideal conditions for kinematic PPP on the left side and compared against some more common real-time PPP product provided by the CSRS Analysis Center through the IGS. And there was an extension of the initial convergence period using the Galileo High Accuracy Service in this case, up to 2.5 hours before that convergence was achieved. But afterward, the positioning precision was able to remain below the target levels of 20 centimeters and 40 centimeters for horizontal and vertical currents. And overall, under these ideal conditions, the Galileo High Accuracy Service provided around 10 to 20 centimeter for mean square error in the 3D kinematic position. Another study evaluated the Galileo High Accuracy Service for real-time positioning, real-time PPP, but under perhaps more realistic obstructed conditions. And in this case, the convergence times were much longer. Larger position errors were found prior to the initial convergence. So what does the future of GNSS positioning look like? Based on recent articles and trends, I think we should be prepared for something more like a PPP-RTK service, or precise point positioning real-time kinematic service being available, rather than thinking about things in terms of PPP and RTK separately. PPP-RTK approach is planned for the Galileo High Accuracy Service in phase 2 in the primary coverage areas. This service provides optional atmospheric information for the user to apply as constraints in our position model. This will help with their accuracy and also to reduce that initial convergence time. But the really nice thing about PPP-RTK is that it's merging some of those concepts from the conventional real-time kinematic processing node and the PPP nodes. So it's still a standalone single receiver user case, but it has as an option for the user those atmospheric constraints, as long as they're operating within some regional type of GNSS network that can provide those high precision. Otherwise, the PPP-RTK approach can instead be used just as the standard PPP approach. So it's really great in terms of the operating range and extending that from a regional to a global space for users. But then also with those developments like extreme computer resolution and constrained atmospheric information, when that initial convergence time can be reduced and start to approach something more like what we're familiar with RTK or network RTK, for example. There are plenty of references. And just put a few of the ones up here that I used today for you to take a look at if you're interested. And with that, I will stop here and thank everyone for the opportunity.
Okay, thank you. Both speakers did a great job. I was kind of amazed at, when we start talking about some of the error sources, I brought into the relativistic effects, and it made me think again. And I remember the GPS signal for 0.07 seconds to get to you. But one thing I never really thought much about, because you don't feel it, that you've moved 32 meters. The Earth is rotated, and that's just kind of an interesting fact that I think people will find important. And I think Brian emphasizing this, the fact that you need to know for the carrier the phase and the ambiguities, which has always been very critical, the better off, the more important we're doing it. Well, we do have some questions, and then we will, right now, we'll get into some of these questions after we take maybe a short little break.